Okay, good morning. It is a great honor for me to officially introduce TianQin to the LISA community. And also, I would like to congratulate you on the adoption of LISA. And I also would like to thank the organizers for having us here. And because of your hospitality and openness, we actually have a very large delegation. So I will go maybe later faster and faster in my talk because I will have a lot of stuff jammed in this 20 minutes talk. So my colleagues will have talks and posters. So if you want to know more detail, please go to them. And they are all Chinese face, very recognizable. And I think maybe at least half Chinese faces in this room are from our group. Okay, so this talk should have been given by Professor Junluo. He is the head of the TianQin project. Unfortunately, his visa has been put under kind of delayed check process, so he couldn't come. But in any case, he has successfully led a very large collaboration, currently consisted of dozens of institutes in China, including some industry entities. So the history of TianQin is actually very closely connected to the personal growth of Professor Junluo. And he is a gravitational experimentalist at the beginning. And since the beginning of this century, he started to have teams working on inertial sensor and intersatellite laser interferometry. And especially in 2013, the team has an inertial sensor, electrostatic inertial sensor, successfully tested in orbit. So this laid down the technology basis for the proposal of TianQin. So at the end of 2013, beginning of 2014, a series of workshops were actually taking place in Huazhong University of Science and Technology. And the original theme was trying to plan for future space-based gravitational experiments, but somehow the topic shifted and eventually it converged to the decision of doing gravitational wave experiments detection in space. But the name of TianQin was officially chosen on March 24th, 2014. But the concept was actually not there yet. So it takes more than a year to get a more complete concept. So the first TianQin paper was actually submitted to the CQG on the 1st of September 2015, about 2 weeks before LIGO detected its first signal. And we were more or less outsiders of the gravitational wave community. So we actually didn't know about the LIGO result until it was officially announced. So this paper was published like January of 2016. So this is TianQin, and I think UCD is a god pick place actually to introduce it. You see on your left, we have 3 spacecraft surrounding Earth, forming a rectangular triangle. And the special feature explained later is a vertical orbital plane. So that's why we call it TianQin, because if you look actually at the crest of the UCD, you see a harp. And it's so that's why we call TianQin a harp in heaven. That's what TianQin means in Chinese. So because we were actually outsiders of the gravitational wave community, so when we were designing TianQin, we actually think in the easier way means we wanted to be close to Earth, so easier for communication, for deployment, and for data transfer. So that's were kind of very primitive requirements that we had in mind. But as we go deeper, then difficulties are becoming to pop up. And the first thing is actually about the sunlight. So we were actually not the first geocentric mission proposed. Very long ago, actually at the same time as LISA, I think, you have this Sagittarius or Omega mission proposed that's actually geocentric. So to see it more clearly, to the left, you have 2 more missions. That's Asteroid GW, and also you have this Lagrangian. Both are using the Lagrangian points of the Sun-Earth system and of the Earth-Moon system. So for the astral GW, you can see the sunlight is always at a fixed angle with the laser links. But for the Lagrange, when it turns, there will always be times the laser links will point toward the sun. So in another word, it means the sunlight will go into the telescope directly, and it makes the gravitational wave detection effectively impossible. So this is the first thing when start to think, and then we realize this is the problem. So the solution from TianQin is actually we just let the orbital plane to stand up. So in this case, when you go from point A to point B, you see in the figure, and from point C to point D, the sunlight will be at large angles with the orbital plane. So these are the places we think would be more suitable for gravitational wave detection. And at other times, the sunlight will come close to the orbital plane and may get into the telescope, and we just give up these observation times. So this actually is the main drawback of TianQin. You only have half the mission time for data collection. That's actually the thing. But of course, there are other things. So because it's very close to Earth, so Earth is not a perfect sphere, it's a potato. So its Earth's gravity will actually interfere with the motion of satellite. In the end, it will interfere with gravitational wave detection. Also, you have this plasma in the near-Earth environment. So this shown here is the worst-case scenario. You have satellites and laser links going through the plasmas, and one may worry, will this also interfere with gravitational wave detection? Actually, about the orbital stability, even after we publish the CQG paper, some people still don't believe, can you have stable orbits with vertical orbital planes to the ecliptic? So these are the things that people keep asking. Also, because we are inside the moon orbit, so will moon eclipse interfere with gravitational wave detection? And also, we have orbital plane standing up, will the large variation in the sun angle interfere with gravitational wave detection? So we have a team led by Associate Professor Xuefeng Zhang to do all this work. The end result is that although these effects might be concerning, but they are not fundamental obstacles for TianQin to detect gravitational waves. So if you want more detail, they have two posters there. But one thing I want to mention is that because the potato Earth, there's actually a lower limit for the sensitivity of TianQin. That's exactly around 10 to the minus 4 hertz. So that's how we choose the sensitivity band of TianQin. So about science, because all the sources that we know are there, and the sensitivity curve for a space-based detector will not be fundamentally different. So you'll see something similar to LISA. So what LISA can detect, we can detect. So, but I also want to add to this importance of the sciences, because with the space-based detector, you can actually look at the very early of the universe, to the first stars and galaxies, to the moon, cosmic moon, and actually to our very nearby home yard. So these, I think, with space gravitational detector, we actually will have a complete new ability to look into the universe. And a question I think you have in mind is that we already have LISA. So why do we need a TianQin? I think you may not say it because you are very polite, but I answered it for you. So we have actually not only TianQin, not only LISA, there's also Taiji, and there's also DECIGO. So comparing to these missions, the TianQin is sort of unique because we are only one with geocentric orbit. We have fixed orbital plane, and we have intermediate arm length. So which means the response of TianQin is actually fundamentally different to that of LISA. And the sensitivity band of TianQin is also different from that of LISA. So you can see that here, to the left, you have two sensitivity curves. The red is TianQin, and the dashed is LISA. So in the lower frequency, TianQin appears to be better. Don't be fooled by that, because we are actually less advanced, so we use an analytical formula to draw that. So it's not true. But what you can see that LISA is more sensitive in the lower frequency end and Tianqin is in the higher. So this translates to different discovery space for the two detectors. So on the, for the two round circles on the right, you can see that the outer circumference of the circle is the normalized capability if we put the two detectors together to do joint detection. And the blue and the red are the Tianqin and LISA to their individual detections. So you see for heavy sources, LISA will dominate the contribution, and for lighter sources, Tianqin will dominate the contribution. So I wish to convey to you the idea that Tianqin is not a LISA prime. Tianqin is a different detector. So that's the first thing. And the second thing is actually having another detector in space actually adds to the science. So this is for stellar mass binary black holes. So Tianqin and LISA both have their own advantages and disadvantages. But if you put them together, the discovery space is much bigger. So one inconsistency you may notice is that you are very advanced LISA, so you are planning for 2035, and Tianqin is much behind, and we also going toward 2035. How is this possible? So I cannot answer you. So I have the technology colleagues behind, please go and ask them. But we do have a roadmap. So this is called the 0123. We do different steps of experimental satellites for two purposes. One is to keep ourselves funded. The other is to move on the technology step by step. So most importantly, it's initial reference. The other is laser interferometry. So for the initial reference, we actually started on 2001 and 2013, the first in-orbit test, and then that laid the foundation for Tianqin, and then we coming this whole way. So this is the current status. I don't know the details, but the bottom line is that some of them are actually got to the requirement of Tianqin, and some of them are maybe one order away, but for more details, please go to these talks and posters. And for laser interferometry, we started on 2002, and then on 2010, 2015, we had the prototypes built. And again, with Tianqin 1 and Tianqin 2, they also made progress on various sub-key technologies, and for more details, I also refer you to these posters. So we also carry out data analysis for all the major gravitational wave sources. So basically, we do it everything by ourselves. We actually a small group on this part, and we have two students currently studying in the Europe. So they will have two posters talking about data analysis, and we also want to test our data analysis capability. So we built it's not called, but it should be called Kludged software that is able actually to simulate coordinated data from all three detectors currently, Tianqin, LISA, and Taiji, because gravitational wave coming, then all the detectors should have a very precise timing between the detectors. So for the experimental satellites, I mentioned that we currently have the Tianqin 1 flown, so it's launched. I won't bother you with the detail. Launched on the end of 2019 and finished beginning of 2021. It finished all the design goals, and we are happy. The number is not there yet, but it proved that our technology does work in space. So currently we are working for Tianqin 2, and it's mostly like GRACE and GRACE follow-on like missions. So it's used for testing satellite interferometry. So it is expected to be launched in 2026. Okay, so this comes most important slide of this talk. I come here actually to call for international collaboration, because with more detectors, it not only adds to science, it is very important for us, Tianqin, to get support from the government. So I know there's obstacles, but there are practical ways that you can actually help or support TianQin. One is through the International Advisory Committee. Currently, this is by invitation and by recommendation only. So thank you, Vitaly already there, and I think Martin is already here. Thank you for already be offering like great help in this regard. And we also have many of you in the audience. I know you probably don't know me because you have collaborated with our very smart young guy, Yiming Hu. He's a student of Martin. So in various TianQin science papers and data analysis paper, and I also want to thank you very much on this. And lastly, we actually want to extend on this many things that you can help us do, like help training our students, and we can apply for joint grants, or maybe if we want to go into more formal, we can sign MOUs. So I also want to do an advertisement. We also have TianQin workshops. So we didn't do it so regularly. The first year is 2014, and we stopped for a few years due to the pandemic. But we revived it this year and had it in April in Hong Kong. And we actually want to have it overseas to get more people to attend. So please consider TianQin in your papers and report your result in the future TianQin workshops. With that, I stop here and thank you very much.
All right, we have plenty of time for questions. Oh, here's one right up front. I'll go ahead and use my mic.
Thanks. In that orbit, do you need to do periodic station keeping? And if so, how often?
So because we have 3 months on, 3 months off, so during the 3 months off period, we can do a lot of things if necessary. So because we already lost half time, we try to do everything, every maneuver in the other 3 months.
Okay, we have one back here.
Thank you so much for your talk. So I have the following question. So there was a LISA Pathfinder mission which has been very successful and has been a kind of motivational, making a case for the future success of LISA, so saying that it's going to be feasible. So my question is, has the success of LISA Pathfinder been in any ways useful in projecting the plans or supporting the case for TianQin mission?
Okay, I don't think we are ashamed of saying that we learn a lot from LISA and also from LISA Pathfinder. But the technology you built belongs to yourself. We have to develop our technologies. So I think some of the details we will not be able to get, but the ideas we can learn from you.
Thank you.
Do we have any other questions? I can't see because there's this really bright light in my face. Kelly.
Hey, I have 2 questions. One is, during the time off, are you affected by radiation pressure? I'm not talking about solar wind, but just pure radiation pressure.
You mean the sunlight, the radiation pressure? I think probably yes.
Okay.
Yeah.
And then the second question I had is, are there sensitivity curves sort of released so that we can do some analysis ourselves or estimates?
Yes, so currently we have just analytical approximations, and it's in basically every of the TianQin science papers. You can just take it from there.
Okay, let's thank our speaker again.